In this video, we're going to talk about the energy that's stored in a capacitor that has some charge on it. So in order to do this, we're going to start looking at putting a capacitor into a basic circuit diagram. So what we would have here is we would have some source of potential, because we do have to then apply this potential to our capacitor. Remember, that's like applying a hill here. So we draw this symbol, which is the symbol for a battery. So this is a voltage source. And that's like a battery. And the longer line is positive and the shorter line is negative. Separate from that, we have the two parallel lines, and this would be our symbol for a capacitor. And so that's our typical circuit diagrams. And so what we're going to say is, okay, let's say I want to apply this voltage to this capacitor. And again, what that's going to do is create this hill, of different energies. This one side that's at positive voltage is the higher hill, the lower side is the lower hill. And so what we do is we just draw our wires connecting these, and we assume perfect wires. So what we mean by that is that it's completely level ground. So all parts of a wire are at the same potential, which, remember our analogy, which means that they're basically at the same height. It's like level ground. So if I have some amount of voltage over on my positive side, then all points along this wire have that same potential. So that would be the potential on the top plate of my parallel plate capacitor. And likewise, now I have, the opposite voltage on the negative side of my battery or my power supply. Very often that's the grounded side that's at zero, but not always. And every point along there is going to equal our same voltage. And so we have now a voltage difference. If we have a voltage difference at our power supply, then over here, we now have that same delta V across the capacitor. So that's a very basic circuit. And we're going to make those more complicated as the modules go on. But that's what it looks like when we say we've applied a voltage to a capacitor. And so if we think about this in terms of energy, remember that voltage, right, is simply going to be equal to our energy per charge, right? So that's some amount of energy per charge. So if I have a voltage across a capacitor, and we have this previous result that C is equal to the charge on the capacitor over delta V, then that's going to allow us to talk about the energy on this capacitor. So we're going to want to focus in on this video on the energy on the capacitor. So to do this, first I want to make a clarifying thing here, that this Q is the charge on one plate. So it's the magnitude of the charge on one plate. When we did that derivation, it was related to the charge density on each plate and was the absolute value. So this plate, for example, since it's at the higher voltage, it's the higher hill, that would be my positive Q, and this lower one would be at negative Q. The net charge on the capacitor is neutral, but there's a charge separation that creates this hill between them, and then we have that energy from that charge. So in order to talk about that value, I'm just going to go ahead and rewrite this capacitance equation in terms of that same little test charge delta V, small q over delta V. And so now we can talk, and we look here at the work done to add some small amount of charge, dq, to the capacitor. If we can find that value, then remember that the magnitude of the work done is going to be equal to the energy change, so the change in energy. So in order to do that, we want to remember this and rewrite this result from up here, the relationship between energy and volts. So we can say that the magnitude of the work done and the magnitude of the energy change, so d delta u, to move a tiny bit of charge, now I'm going to be working with this dq, is going to be equal to dq times delta v. That's the amount of change in energy that I'm going to get from moving or adding a little bit of dq to my capacitor. And so now I can go ahead and rewrite delta v using my capacitance equation. And so I end up here with dq times q over c. And so to solve this for delta u, I can then integrate this q over c dq. And I want to integrate it from one side to the other. So I want to kind of add up my total amount of charge that I'm going to be adding. So I might start by adding, I start with no charge, and then I add up to some capital Q charge. And then that's going to give me my total energy for some total charge Q. And you can see when I go through this, what happens, besides just sort of multiplying the equations like you might have been inclined to do, when you actually have to think about it incrementally in these small little dq's, this integral gives us a 1/2 that comes out. So this ends up being 1/2 q squared times 1 over c, evaluated from 0 to q. And so we get this result that delta u is simply equal to 1/2 q squared over c. And so we have that nice result, which we can then put a box around. And this is the total energy stored on a capacitor in terms of the amount of charge. And so, as expected, the more charge on the capacitor, then the higher the energy that is stored. We can rewrite this in different ways using this expression for C equals Q over delta V. So we could write Q equals C delta V and plug that in. And so that would give us delta U is going to be equal, and we can see that I would get 1/2, and then I would have C delta V quantity squared over C. So I end up with 1/2 CV squared. I'll write that as C delta V squared. And so we end up with another way of writing these. So these are all equivalent ways of writing the energy. And then lastly, I can also write it eliminating my capacitance entirely. And I can plug in for the capacitance, and I can see that if I plug in C equals Q over delta V, then what I get here is that delta U is simply equal to 1/2 Q delta V. So all of these is just equivalent equations that are simply substitutions using the capacitance definition to rewrite them in ways that might be useful. The fundamental idea, again, being that the energy stored depends on the total charge on the capacitor, and the total charge on the capacitor depends on, the height of the hill, so on that delta V, and that when we go through adding up the work done by adding a little incremental bit of charge at a time, that integral brings out this factor of 1/2 in this equation. I hope this helps.